Signal Acquisition Cuervo. Project number 71 in NASA's Explorer program was a solar terrestrial space weather mission with important scientific objectives. Engineered to determine the elemental and isotopic composition of matter, the origin of the elements, the formation of the solar corona, and the acceleration of the solar wind. Headed by Caltech and JPL, the Advanced Composition Explorer, or ACE, would help us better understand the Sun moving into the 2000s. Spin stabilized and with an estimated attitude accuracy of plus or minus 0.7 degrees, the probe used its 443 watts of peak power to allow its decks of instruments to collect data. The octagonal probe, weighing 785 kilograms, was 1 meter high by 1.6 meters across, but would have a wingspan of 8.3 meters when its panels were fully extended. The bus of the probe would also take with it hydrazine fuel, 190 kilograms of it, to help maintain orbit during its planned mission duration and beyond. Real-time S-band data sent to Earth would stream at 6.9 kilobits per second, while data collected and stored on 2 gigabits worth of solid-state recorders could be sent back at 78 kilobits per second, just faster than terrestrial dial-up of the time. ACE's propulsion system would direct the probe to a special orbit after launch, keeping it at a specific place in space, but we'll cover that later. A collection of 9 sun sensors and science instruments would make up the probe's data collector. They were made up of the following: SWIMS, or the Solar Wind and Ion Mass Spectrometer, measuring solar wind composition, with detection ranges of 4 to 60 AMU, or atomic mass units. SWIX, or the Solar Wind Ion Composition Spectrometer, measuring the elemental and ionic charge composition, temperature, and mean speeds of all major solar wind ions, from hydrogen at 145 km per second to iron at 1532 km per second. ULAIS, or the Ultra Low Energy Isotope Spectrometer, measures ion fluxes over the charge range from helium through nickel, about 20 kiloelectron-volts per newton to 10 mega-electron-volts per newton. SEPICA, or the Solar Energetic Particle Ionic Charge Analyzer, measuring the ionic charge state, energy, and nuclear charge of incoming ions. The other 5 instruments on board ACE would feed a new NOAA NWS website for the Space Weather Prediction Center, which as of today is still up and running. The instruments showing data on this website allow for advanced warning of geomagnetic storms, another natural hazard for us here on Earth. The instruments include the following: MAG, or Magnetic Field Monitor, measuring all 3 components of the magnetic field, with fast Fourier transfer data as well. EPAM, or the Electron, Proton, and Alpha Particle Monitor, that measures interplanetary particle fluxes with a wide dynamic range and directional coverage. CRIS, or the Cosmic Ray Isotope Spectrometer, measures all stable and long-lived isotopes of galactic cosmic ray nuclei from helium to zinc. SIS, or the Solar Isotope Spectrometer, measures the various elemental and isotopic composition of solar energetic particles, anomalous cosmic rays, and interplanetary particles up to 100 mega-electron-volt per nucleon. Finally, SWEPAM, or the Solar Wind Electron, Proton, and Alpha Monitor, provides high-quality measurements of electron and ion fluxes in the lower energy range, sub-1240 electron-volts or sub-35 kilo-electron-volts for ions. ACE would reach its intended point in space atop the Delta II 7920-8 rocket, from its source at the time, McDonnell Douglas. The 7920-8 designation meant that the rocket was a 7000 series with an RS-27A Kerolox engine booster, 9 solid rockets attached, 2 for its AJ-10 118K hypergolic upper stage engine, and 0 for no third stage being used. The final digit, 8, denoted the fairing diameter in feet, with 8 pertaining to the older Delta rockets.
3, 2, 1. Have ignition and liftoff of NASA's Advanced Composition Explorer, looking to study the solar wind and further our understanding of the universe.
The A spacecraft launched on August 25, 1997, from the Kennedy Space Center at Cape Canaveral, Florida, at 1439 UTC, on its way to Lagrange Point 1. Lagrange points are positions in space between any 2 orbital bodies where things that get there tend to stay there without much change to their orbits. Technically, the the gravitational pull of the two bodies at that point will be equal to the centripetal acceleration required for a small object to move with them. Reduced fuel and easier stability for attitude adjustments are hallmarks of the Lagrange points. There are 5 points where this special orbit occurs for small objects. 2 are stable, L4 and L5, while the others are unstable. L1 in the Sun-Earth system provides an uninterrupted view of the Sun, with a small halo orbit about the L1 point. L3 is always behind the central body. Stability at L4 and L5 is given only when the ratio of mass is around 25 times larger between the two large masses. Lagrange points can also be calculated for other bodies in our solar system. For example, in a Sun-Jupiter system, L4 and L5 are the location of both bands of Trojan asteroids. For ACE, the journey to L1 would see the delta upper stage pushing it out to 1.5 million kilometers, leaving ACE about 1.5% closer to the Sun than Earth. If ACE were to turn around and look at the Earth, an amazing sunlit view would always be available for certain platform instruments with the Earth rotating in front of it. ACE is by no means alone at L1. In the past, NASA's Genesis, the International Cometary Explorer, and ESA's Vega Pathfinder all called it home. Currently, however, ACE has SOHO, WIND, and Discoverer as neighbors at L1. We will have videos about those probes in the future. Part of the science collected by ACE includes impressive early images of the Sun's flares and corona. Also, continued data on the solar wind and its particles, along with interplanetary coronal mass ejections, have come from ACE. One area in particular where ACE data was used is in analyzing the relative solar wind speed during solar maxima and minima. For the first time, data on sunspot counts used to describe minima was seen to not affect the solar wind speed until a general decrease of geomagnetic effects was also observed. Scientists from JPL and other space weather specialties discovered that coronal holes were producing the high solar winds experienced at minima, and at least in 2007 and 2008 were having more of an impact on Earth. ACE was also used to measure the creation and travel of anomalous cosmic rays. These are particle rays that begin as solar wind particles that pick up ions as they traverse interstellar space and rebound off the solar wind's termination shock at the edge of the solar system. They then return back through interstellar space and can be differentiated from galactic cosmic rays given their energy. Finally, as stated earlier, ACE is still creating data for NOAA's Space Weather Prediction Center. Available to the public, it can help alert all of us of incoming coronal ejections or variances in the solar wind that may be troublesome to electronics near and on Earth. Other science fields can also use the data, coupled with new astronomical data, to better predict solar activity in the future, given the many probes that are also analyzing solar particles. Thanks for watching. If you enjoyed content like this, please consider subscribing, liking, sharing, and commenting on this and other future videos. Also, remember to follow us on Twitter and Instagram for more space content.